everyone. So it's more hormones today, more endocrine stuff. All right. You know this, so the neuroendocrine system, this is just let's start in the hypothalamus, let's start in a hunk of brain, and let's communicate with the body outside of the brain. Let's get into the periphery from behind the blood-brain barrier and the sort of cutoff man for the plate, right? So if this is baseball or softball, and you're out in the outfield and you throw it to the shortstop and the shortstop throws it to home plate or whatever. That's sort of how this works. It's not just one gland or one organ or one tissue doing all of the work. There's a relay race that happens, and that same relay race, the same phenomenon of a relay race, happens in cell signaling cascades. But before we even get to the cell signaling cascade, it's the neuroendocrine system. So the stuff. It's we talked about this on whatever it was, Monday. Water regulation, there's sexual stuff, there's thirst, there's appetite, there's tons of metabolic things, cell survival and hypertrophy and atrophy and apoptosis and blood sugar, insulin, glucagon. There's sort of feeding behaviors, the appetite stuff, getting into that blood pressure, if we're getting into in part into the kidneys. And there's just so many functions that your hormones do. And the neuroendocrine, right? It's neuroendocrine. It begins up in the hypothalamus, which isn't a gland. It's just a little hunk of brain. The pituitary is a gland. The hypothalamus is not a gland. So when you're looking at like glands in the body and it shows a hypothalamus, that's just regulating the glands. And but you know what these things do? So we've talked a fair amount about the pituitary, the thyroid. There's a bunch of axes, right? So the hypothalamic pituitary thyroid axis, the hypothalamic pituitary adrenal axis, get into that adrenal cortex to release cortex, cortisol, hypothalamic pituitary gonadal axis. The parathyroid isn't one of those axes. There's four glands, the parathyroid glands. There's four of them. You put them all together, it's the size of a Cheerio, right? It's not like a huge thing. If you have low blood calcium, you will get your parathyroid hormone released, and you're going to start inducing osteoclast activity, and the bones are a wonderful storage silo for calcium. So serum calcium regulation. But a lot of this, you're recognizing a lot of them, I'm sure. So the origin of endocrinology, you remember Arnold Berthold, our German zoologist, 1849, and he starts doing his castration experiment, and that's when he published it. I don't know when he was doing all this stuff or when these thoughts occurred to him, but in 1849 is when he gave his big presentation about yeah, okay, we castrated some of them, we put them back, but we threw them up in the abdominal cavity, and they get more blood supply, put them in there, and they revascularize at the end of their life. Dissect them, and you see this vascular supply that is no matter where you put them. And other ones, you switch who has the testes, like trading Pokemon cards or something. And so this is the 1849. This is the real foundation of endocrinology. A lot of stuff followed him. It wasn't just, okay, we have chickens, fine, we get it. All the animal kingdom works in the same way. This article talks about a lot of these follow-up experiments where non-breeding sparrows and the aggression, I mean, they sort of rerun this experiment over and over and over across the animal kingdom, and figure out how the testes testify to virility, right? How they develop the physical form, stuff like that. So axes. All right, let's get into some axes. If I ask a question, what regulates X? solve for X, whatever. What regulates X? It's going to be the hypothalamus. Now, you could make a strong case for the pituitary. Well, the hypothalamus controls and the pituitary regulates. Okay, whatever. Who cares? Matters of nomenclature. But throughout the semester, we've had a lot of go-to answers. If you didn't know the answer to a question in the first block, you could say, because size principle, or because specificity of adaptation. And throughout the whole semester, you could probably say, because self-preservation, or because survival, or something like that. In the same, when we're talking about biomechanics, you could say because moment arm. So there's a lot of go-to answers, and hypothalamus is being added to that list of why do we do this, or how. It'd be a mechanism. So how is mechanism, not purpose is why. How does this happen? Hypothalamus. I mean, that's a really good place to start. I used to play Trivial Pursuit with my friend Tim Walker, and this is the 1981. It's the very first ever version of Trivial Pursuit. It's called the Genus edition, not the Genius, but the Genus edition, and it came out in 1981. And Warren Beatty, this guy over here, was huge in the 80s, enormous in the 80s. That year was sort of the peak of his life, and there's all of these entertainment category things, and I didn't know the answer of any of them because it was from like the 70s and stuff. I wasn't alive, but there were so many answers that were Warren Beatty that whenever anyone asked a question I didn't know, I just say Warren Beatty, and I'd get it right some of the time. So you can do that on the test. When the test comes, you can do that with the hypothalamus, or you could do it with specificity of adaptation, or something that's one of our go-to answers. So again, with the hypothalamus, if this helps you remember what it's doing, what its function is in the body, Van Ness's 6Fs, right? So it's fight or flight, and fright, and food, and fluids, and we'll say fornication, right? So it does a lot of things, and it communicates directly with the pituitary. Now, there's an anterior pituitary, there's a posterior pituitary. Technically, it's not on any of these diagrams, but there's actually an intermediate pituitary. It releases melanocyte stimulating hormone. I'm unaware of anything else it does. The anterior pituitary and the posterior pituitary, especially the anterior, these are the big players. And this is actually rotated a little bit, should be rotated more. But so you can see where the hypothalamus is, and just below it, just south, that's where the pituitary is. And the anterior pituitary, this front one here, that is connected to the hypothalamus through blood vessels. So there's this capillary network. So it goes from the hypothalamus to the anterior pituitary through blood vessels. It doesn't have to go into systemic circulation. It is a direct route. It has its own access road. It doesn't go into systemic circulation, but it does get there through blood from the hypothalamus to the anterior pituitary. In the posterior pituitary, it's not blood vessels. In the posterior pituitary, it's nerves, right? So the cell bodies of these nerves live in the hypothalamus, and then they descend, they go down the infundibulum, right? So on this last picture, right, it's called, or I guess two pictures ago, that pituitary stalk right here, or the infundibulum. Sometimes people will say the infundibular stalk, but whatever, this thing. And this is that point of connection between the anterior, where those blood vessels live, and in the posterior, where those nerves live, the infundibulum. And so the nerve terminals are in the posterior pituitary. So stuff the posterior pituitary releases, oxytocin, vasopressin, stuff it releases, it's made in the hypothalamus and released in the pituitary. In the anterior pituitary, it is different. It is hormones going through the blood, through that little tract, that little vascular tract, and then into the pituitary to tell it what to make, so it makes new things. And if we lost this hypothalamic pituitary axis, it begins at the hypothalamus, goes through the pituitary, and ends wherever, right? In the liver, it could be, if it's growth hormone releasing hormone in the hypothalamus, blood supply to the anterior pituitary, release growth hormone. Growth hormone makes the liver release its IGF-1, insulin-like growth factor 1. So the hypothalamic-pituitary-whatever axis, if we lost this relationship, untreated abnormalities of the axis are incompatible with life. I mean, it's just everything we do. It integrates all of our functions. It regulates everything we are doing, metabolism and temperature. If we're looking at the hypothalamic pituitary thyroid axis, we're looking at regulation of temperature, metabolism, and just a bunch of this stuff it releases. So here's how you think of it, right? So this is the hypothalamic pituitary whatever axis. If you're familiar with The Office, you recognize this slide. If you've never watched the American version, the only good version of The Office, then you will not know what the hell's happening here. But David Wallace, for a time, let's say this is in the era of The Office, when David Wallace, he's the CEO, and so he gives Jan instructions. She's some sort of general manager. She manages several branches and whatever. She doesn't work in any branch. So David Wallace, the CEO, he would be the hypothalamus, right? He's ultimately in control. What he says goes. And he tells Jan, all right, go tell branch manager X, whoever the branch manager is, to do this thing, right? So Jan is going to be pituitary. So we have David Wallace. He's going to be the hypothalamus, tells Jan, the pituitary, to tell the regional managers, the branch managers, what to do, whether it's Dwight or Andy, whoever it is. And then they'll go tell the local tissues how to behave. And so maybe a local tissue could be the heart beating faster or slower. Maybe a local tissue is skeletal muscle and protein turnover, right? Maybe a local tissue, whatever it is, some metabolic thing. And maybe it's something to do with hydration and sodium retention or whatever. You have your CEO telling your have a president or general manager or somebody to tell the branch managers what to tell the tissues. That's the hierarchy that we see with the HP whatever axis. And so all these axes, hypothalamic, pituitary, adrenal axis, corticotropin, sometimes you'll see an H in there, corticotrophin, whatever, corticotropin, releasing hormone comes from the hypothalamus, adrenocorticotropic hormone comes from the pituitary, and then the anterior pituitary, and then out of the adrenal gland, out of the adrenal cortex, you get your cortisol. Hypothalamic pituitary thyroid axis, same thing, hypothalamus, pituitary, and then let's go to the thyroid, right? Let's get some T3, let's get some T4 going. Hypothalamic pituitary gonadal axis, so gonadotropin releasing hormone, luteinizing hormone, a follicle stimulating hormone, and then you get down to testes and ovaries after that. Hypothalamic pituitary liver, we talked about that one. Somatostatin, that's the opposite of growth hormone, releasing hormone that says go ahead and stop now, don't release growth hormone. And I'm seeing some comments from The Office. I think everybody loves it. If you don't love The Office, you have some psychoses, or there's something wrong. It's fine not to like the British one, like the English one. I just didn't find that one funny at all. It's like a Bob Dylan song where you hear Bob Dylan do it and like that's not good, and then somebody covers a Bob Dylan song and immediately you realize it's an amazing song. Whoever covers Bob Dylan songs, the songs themselves are good. I think that's the English version of the Office, where yeah, there was a nice song there, but they just executed horribly. Bears beats Battlestar Galactica. Okay, let's move on. It seems like my Office analogy is sort of registering a little bit. And if you haven't watched The Office, that's your assignment for the semester before studying for the test to get through. I didn't find the first couple of seasons all that interesting. I thought it ended so much better than the first couple of seasons. I thought were so sorry. It doesn't matter. So hypothalamic, pituitary, whatever axis. The posterior pituitary, not much going on here. ADH, antidiuretic hormone, that's vasopressin. Arginine vasopressin. AVP, you'll usually see it as ADH. That's the old word for it. Antidiuretic hormone, ADH. It's the exact same thing as vasopressin. It's just a different name. ADH is not a good name because there's two ADHs. Alcohol dehydrogenase. That's the ADH. If you see ADH, we're probably, at least I would be talking about alcohol dehydrogenase. And so AVP or vasopressin, arginine vasopressin, that is this one, it's anti-diuretic hormone was a fine name for it because anti-diuresis. Let's not lose fluids. Let's hold fluids in. Remember, that's the thing alcohol blocks is vasopressin, and then oxytocin. So that's the stuff the posterior is releasing. Everything else is coming out of the anterior pituitary. So that's all the blood supply stuff. Just remember the difference between neurotransmitters and hormones. We're going to talk about the classes of hormones. That's today, but hormones tend to be longer range. They don't have to be. Hormones don't have to be long range. Endocrine means long range. A classic endocrine hormone, an insulin or a growth hormone or an epinephrine or a glucagon or testosterone or estrogen. I mean, you just go down the list of these endocrine hormones. They get into the bloodstream and circulate around and eventually arrive at their destination. They migrate for a while. But you can have paracrine signaling. You can have autocrine signaling. We talked about that stuff. I'll explain a little more today, but intracrine signaling if you're inside of the cell. Steroid hormones go inside of the cell. That's where they have their activity. But we're not really going to talk about intracrine. Mostly what we're going to talk about is endocrine, autocrine, and paracrine. But hormones, this isn't all or none. This is concentration based. Hormones, concentration based. How much of the hormone do you have? Do you have a ton of insulin? Do you have a tiny bit of insulin? Do you have a ton of testosterone? Do you have a tiny bit of testosterone? The effect is relative to the amount. Nerves, the all or none principle, does this nerve depolarize and does exocytosis happen? That's all or none with a neurotransmitter communicating its message. But even there's some room for something like if you're on the sarcolemma and it's a bunch of acetylcholine receptors, and do you have more or fewer receptors? But for the most part, neurotransmitters, we're talking all or none. Hormones, concentration. Hormones in general, again, just they're chemicals, they're substances, they're messengers and molecules, whatever, and they're mostly released by glands, but other cells too. Muscle can release it, fat releases it, a liver releases it, kidney, your stomach. I mean, so these things that we think of as organs, your stomach, an organ. You don't think of, if somebody said like name some glands, you would go, oh, kidney and liver and stomach, and you wouldn't say that. But the stomach is releasing ghrelin, and that's a food seeking, a sort of appetite hormone. It works on the hypothalamus, and we'll talk about that a little bit later. Some of these, when we talk about why does weed give you the munchies, right? It's what happens at the hypothalamus, and we'll get there. But leptin and ghrelin, these things are working on the hypothalamus to affect feeding, to affect whether it's food seeking sorts of behaviors or it's just appetite. How much do you go to the buffet, and how much do you put on your plate on round one? But cells in the body are making these things, and that's really what glands do. But other tissues are doing it too. It's not just glands. Now, normally, if we were live and I could look at your smiling faces, maybe sleeping faces, some of you have probably started watching The Office already. Yeah, I would have you explain to me the different hormone classes, the two hormone classes. I'll talk about eicosanoids in just a minute. But remember, amine, peptide, protein. You can call these three, lump them into the same group, and just call them polypeptide or call them protein or amino acid hormones, however you want to phrase these things. Commonly in the literature, they say polypeptide. But this is just strings of amino acids. Sometimes it's one amino acid, right, where we are epi, norepi, right? Sometimes it's a few amino acids, glycine, leucine. So we see these multiple amino acids. Sometimes it's a protein hormone and like growth hormone, 191 aminos. That's a big, long hunk of protein. So it just depends on the size, but all of these work in the same way. First off, they work quickly. These polypeptide, let's just call them polypeptide. But if I say protein, if I say amino acid, whatever, I'm talking about the same thing. But polypeptide hormones, these are fast acting, pretty short lasting. There was a professor here. He moved, I think, to Idaho a few years ago, a couple years ago. He was in the AT program. He had what he thought was some sort of placebo. He thought it was a little demonstration needle. It was a little EpiPen. He put it in his, like, during class. He was talking about an adrenal response or some, I don't know what he was exactly, what the lecture is about. All I know is that he put the thing in his leg and gave himself a shot of epinephrine. And he just, his heart, I mean, he's sweating and his heart rate went crazy. He's like, "Oh, I gotta lie down." He's in the middle of class. And what a spectacular demonstration by a professor of, let's put our health on the line here and see if we can really give the students something to remember. He didn't do it on purpose, but it didn't last forever. He returned to teaching. He just lied down for, let me lay down for 5 minutes. That's it. And he returned to the class and started teaching as soon as his heartbeat went back down. So Abby remembers hearing about that. I don't want to name the person, just in case he's embarrassed. I don't think he would be embarrassed. I'd be pleased to have been the one to have done that story, but I don't know what his emotional standing is on that experience. So but these things, it's a great example for how short-lived these are. There's going to be some proteolytic enzymes that'll break it down. This is cell surface stuff. These don't go in to the cell. These bind to cell surface receptors, amine, peptide, protein. All of these things, they behave in the same way. It's very fast. It's cell signaling cascades. They can't just go through a sarcolemma, a cell membrane. They can't just go through the cell membrane. They have to go up to the cell membrane and sort of knock, right, and ask, like, hey, is Barbara inside, or whatever. They have to go up and relay a message. It's like a middle schooler relationship. And a steroid hormone, these are made from cholesterol. This is the cholesterol backbone of whether it's cortisol, aldosterone, testosterone, progesterone, whatever these steroid hormones, it's cholesterol. They're made from cholesterol. And cholesterol is like 30%, give or take. It depends on the cell, it depends on the creature, it depends on the person, if it's a person. But let's just say it's roughly maybe 30% or so of this phospholipid bilayer. And so you have these hormones that are made of the same stuff. They just go right through. So when I was in, this was middle school, I had a girlfriend who had beads on the door. I think, I don't know, maybe some of you have like beads instead of a door. There's beads. If the door is closed, you can't just walk through a door, right? But you can walk through beads. It's just like, and you make that little noise as you go through them, and you blink, right, so it doesn't poke you in the eye or something. That's steroid hormones. They go right into the bedroom. They go right into the cell. They don't sit there and knock and relay messages and pass notes. That's for proteins. That's for these polypeptide hormones. Steroid hormones go right in because they're made from cholesterol. Now, if we're going to say there's a third class, I like to call this third class immune system, chemical stuff, not classic hormones. But if we call the third class hormones, fine. Okay, we have polypeptide hormones, right? Those are proteins and some glycoproteins, stuff like that. Maybe you can get a little bit of carb in there, but they're all proteins, right? There's a bunch of amino acids. And steroid hormones, right? Those are cholesterol. Now, cholesterol isn't fat. Cholesterol is not a string of carbons in the way that a fatty acid is. Cholesterol it's very waxy. There's no calories in eat all the cholesterol you want. There's no calories in it. It's a sterol. It's a OL, an alcohol, right? Has an OH group on it. You can see that little little OH group. So it's a lipid alcohol. You make your vitamin D from it. So you can think of vitamin D as practically a hormone. And bile acid you make from it. And then the steroid hormones you make from it. But it's not the same thing as fat. Eicosanoids, these are fat. right? These are coming from a 20 carbon free fatty acid, that arachidonic acid, which also lives in the cell membranes. Arachidonic acid lives in the cell membranes, but the eicosanoid hormones, whatever, these fatty acids, they have cell surface receptors like the polypeptides. They don't behave in the way that steroid hormones do. So like prostaglandins, leukotrienes, thromboxane. I mean, these different eicosanoids have cell surface receptors just like the polypeptide hormones do. The only ones that leap through that bead door, those are the steroid hormones. But also it's a little bit weirder. The triiodothyronine, that's T3, T4 is thyroxine. That those are your thyroid hormones, T3, T4. Now, those are tyrosine based. It's an amino acid hormone, right? It's polypeptide hormone, but they have nuclear receptors. They have inside receptors. They cross the cell membranes, not in the same way that you notice you're not seeing cholesterol here. That's cholesterol right here, and that's a steroid hormone, right? Epinephrine, right? This is an amine hormone, polypeptide hormone. But this, yeah, we're polypeptide too, right? This is a thyroid hormone, hypothalamic-pituitary-thyroid axis. T3, this is the active one. But this crosses the membrane by transporters. And then it has its nuclear receptors. It also activates PI3K, phosphatidylinositol 3 kinase. We're going to talk a lot about PI3K today in terms of anabolic signaling. PI3K. We'll start to talk about PI3K today. This section, this block, PI3K becomes a really heavy subject. So these, I would say, are sort of the three classes of hormones, where you have polypeptide, right? The proteins that are cell surface receptors. You have steroid hormones, which go right through. They go right through the phospholipid bilayer. They go, if it's muscle, they go right through that sarcolemma and have their cytosolic or nuclear receptors. And then triiodothyronine, T3, T4, right? This is T3, have transporters, and so they have intracellular receptors. And so it's a little bit of a hybrid, this one, of these two, a little bit. Now, testosterone also, steroid hormones also have some cell signaling cascades that we'll talk about in a few days, in a few lectures, not today or tomorrow or the next day. But we will get to this, some estrogen and testosterone and their effect on the cell signaling cascade piece of mTOR, where it's not just nuclear receptors and direct DNA activity. It's cell signaling cascades as well. And so there's more diverse signaling. So AKT, you're going to encounter this a lot as we move forward. AKT, that's PKB, that's protein kinase B. So we've talked about PKA, protein kinase A, in the nerves. We talked about PKA in fat, and we're going to talk a little bit more about that today, about how to mobilize fat. And we'll talk about PKA in carbohydrate. So PKA is catabolic. It was the depolarizing of the nerves, but PKB is anabolic. So PKA, if you're in the liver, you're mobilizing carbs, you're chopping up glycogen and throwing it into the bloodstream. If you're in an adipocyte, you're mobilizing free fatty acids, right? You're going through lipolysis, lipid lysis. You're lysing lipids and putting free fatty acids out into the bloodstream. Let's get ready to burn these things. And glycogenolysis, glycogenolysis, right? Let's lyse our glycogen. Proteolysis, let's lyse protein, anything lysis. And so when we have steroid hormones, yeah, they cross the phospholipid bilayer, and that's inside of the cells where they're going to have their receptors, but they also have secondary effects of cell signaling cascades. So again, we have peptide, polypeptide, this class, a bunch of amino acids, and we have steroid, which is made from cholesterol. So these ones are fat soluble. That's how they diffuse across sarcolemma, if it's muscle, right? Phospholipid bilayer. And the peptide, right? They can't diffuse. These are water soluble. They can't diffuse across phospholipid bilayer, and these ones is usually act through a second messenger on a cell surface. Yeah, okay, let's ignore the thyroid and say essentially like we're always doing this. So just a bunch of amino acids, very fast initiation, but temporary action, right? Hang out on the cell surface, and you're going to have some proteolysis happening. You're going to break these things down. I remember acetylcholine esterase, that thing that breaks down acetylcholine, that enzyme. There's just an ACE that breaks stuff down. With steroids, get these inside of the cell, and there's a little bit more protection. It's Stockton outside for me, and for most of you. It's Stockton outside. And do you want to sleep on your porch, exposed to the elements, and the elements in Stockton are people? Or do you want to sleep inside of your house all locked up, cozy in your bed? Most people would choose to sleep inside of the house, right? So steroids. So these last a lot longer. The effect is longer, not just because of that, but so the peptide. These are fast acting, short lasting, and the steroid. These take a while to have an effect, but that effect lasts a long time. So again, like epinephrine comes and goes. You can do your epi shot, and 5 minutes later, you just want to take a nap. Actually, 5 minutes later. But steroids, I mean, people will do these. I don't know, what's once a week, maybe, for the steroid shots. You can also take these by orally. You can take them by mouth. You can't, like insulin. You can't take that by mouth. You can't like you have to inject these because they're food. It's protein, right? These are just food. Growth hormone. There's no such thing as a pill. Oh, let me take the growth hormone pill. No, it's the same thing as like an egg or a hamburger or something. It's protein. You're just going to use it as protein. It's just amino acids. Over here, this gets absorbed, not in a good way, and we'll talk about that later. So can peptide hormones not cross the sarcolemma, do the sarcolemma? They just, yeah, they're unable to cross. So the peptide, these cannot cross. They're the cell surface receptors. I mean, that's what these lipid bilayers are for, is just to keep out the riffraff. And so the riffraff can knock, right? The riffraff can knock, but it can't enter. These ones can just go right through. So again, there's a ton of glands, and not everything is a gland, a classic gland. So the question about what are oral steroids? Yeah, it's just that they're going to mess up the oral steroids. You can take them. Prednisone. A lot of people will take prednisone. That's a catabolic oral steroid. You can get injections, and you bypass the liver if you inject something. If you take, I promise I'll talk about this, but like if you take D-ball or something, or a lot of people will take that by pill because they're, I don't know, sissies, and they're afraid of a needle or something, and you'll just watch their cholesterol get all messed up. I mean, you are synthesizing cholesterol in the liver, and anything you eat, anything that goes out of your stomach, goes straight to the liver and messes up your lipids. Now, if you're doing like estrogen, you can enhance your lipid profile, but if you're doing androgens, andro, man, genesis, make, so anabolic androgenic agents, that's going to mess up. Well, and I promise we'll get there. So yeah, epi, cortisol. Now, these two things are very similar in terms of what they're doing. So they're sort of both stress hormones. Remember uh, general adaptation syndrome that was wrong, but general alarm reaction that was right? That's getting both of these going. The sympathoadrenal medullary axis, right? That gets epinephrine going. So that's a very fast version of a stress response, epinephrine. I mean, just panic. Have somebody nearly hit you with a car, or have a dog bark when you're not expecting it. That's 3 inches away and is running at you or something. Epinephrine happens fast. Right now, part of it, you'll also eliminate the parasympathetic nervous system, and so vagal nerve activity is vanishes. But epinephrine, this is very fast. Cortisol is not fast, but this is long-term stress. It lingers and lingers and lingers. You're super stressed over finals week, and epinephrine is going to go away as soon as the finals are over. Cortisol isn't. That's going to linger. But they're doing something very similar. They're doing a very similar function. Luteinizing hormone, right? We're just en route to the gonads. Growth hormone, adrenocorticotropic hormone. We are en route to cortisol. There's your testosterone, insulin, and glucagon. We'll talk about those things. This is just another look at the same Hormones, just what glands are releasing these things and what the actual hormones are we're talking about. Now, growth hormone, everyone talks about this, everyone loves this. What if, and we'll go into detail in growth hormone, what it's actually doing. It's cell signaling, is JAK stat, is its signaling cascade. It's unique. Growth hormone is a fascinating one, but there isn't really growth hormones. Maybe there should be an S on there. There's like 100 aggregates of these different variants of growth hormone. And that version that we all talk about, 22 kd, 191 amino acid version, that's like the pharmacological version of it, that doesn't really seem to have the same effects and interactions that some of these aggregates do. Insulin-like growth factor, that how growth hormone is actually working in the body to do hypertrophy. It's a lot of it is mediated through insulin-like growth factor 1. And that's, I mean, especially if you are a lady, right, your testosterone levels are very low, but you might have higher growth hormone than the guys. Maybe not the peaks as high, but if you do some mean value, your growth hormone levels might be higher. So looking at how you recover from exercise and what happens in a weight room to put to Humpty Dumpty yourself back together. It's a lot of growth hormone, and from growth hormone, insulin-like growth factor. Remember, factors are always proteins. We talked about nerve growth factor that binds to track A. Brain-derived neurotrophic factor binds to track B. Insulin-like growth factor, right, has its own IGF receptors, but it can bind to insulin receptors as well because it's insulin-like. It looks like insulin. Now, again, most hormones come from glands, atrial natriuretic factor or peptide, from the heart. So that's if we have something come from the heart, from the liver, right? Insulin-like growth factor, and it's not the only, renin from the kidney, but that's not the only spot you're going to get IGF from. Now, I'm unaware of another spot in the body that you get ANP or ANF from, atrial natriuretic factor from, other than the atria, right? The atria, those chambers of the heart, really stretch out those chambers, you get some, maybe some other cell, and I just don't know that. I just haven't, seen it. But for the most part, there's particular hormones that come from particular areas, but sometimes there's some overlap. Insulin-like growth factor, it's not all coming from the liver. Now, this is a pancreas right here. This sort of weird looking thing is a pancreas. There's a gallbladder. So go eat a bunch of fat and let's dump some bile into our intestines and let's emulsify some fat. Here's some duodenum over here. So this is, inside of your insides. You have a pancreas. Now we have alpha cells and beta cells and delta. We only talk about the alpha and beta. The beta cells in the pancreas are producing insulin. Alpha cells are producing glucagon, but the beta cells, this is where insulin is coming from. And this is insulin, right? It's a peptide hormone. It's a bunch of amino acids. Each one of these little circles is an amino acid. Then it goes, and so being a polypeptide hormone, it has to bind to a cell surface receptor like this, right? There's an insulin receptor, and downstream from insulin, you're going to have a bunch of signaling. It's going to, something's going to happen downstream from whatever binds. So you see like insulin receptor substrate, and then PI3K, and then PKB, protein kinase B, and then downstream from PKB, tons of anabolic stuff. One of those things downstream from protein kinase B. Remember, kinases are enzymes. And then there's tons of them. There are tons of kinases, and kinases phosphorylate stuff. Let me attach a phosphate to something. I phosphorylate you. I attach a phosphate to you. That's what kinases do. Protein kinase A phosphorylates what is generally catabolic stuff. Protein kinase B phosphorylates what is generally anabolic stuff. Insulin, anabolic hormone. Glucagon, catabolic hormone. Guess which one each of them works through, right? Glucagon does a bunch of pKa signaling. Uh, Insulin, anabolic, does PKB signaling. And so GLUT4 translocation, let's move that little guy up to the surface and bring sugar into the cell. That's downstream from PKB. And so once you get far enough into the insulin signaling cascade that you've activated protein kinase B, Now PKB is going to phosphorylate some very anabolic stuff. Let's translate proteins. Let's make new proteins. And bring sugar into the cell. It's going to shut off catabolic stuff. I mean, PKB does a lot of things, and we'll talk about it at length. But if you are an icosanoid or a protein polypeptide hormone, this is how you work, right? Unless you come from the thyroid, then you have some transporter that gets you inside. Steroid hormones just go right in, but everything else you have to bind to a cell surface receptor, and you get this signaling cascade that goes. It doesn't have to go to the nucleus. That's a common destination. That's not the only destination. Where this cascade ends. Maybe you're going to the ribosome. Maybe you're going to GLUT4. Maybe so there's the other destinations where the stuff ends. So now this is our membrane, right? This is our cell surface, our let's if it's muscle, this is a sarcolemma. And we have these hormones that are specific shapes, and they're going to bind to a specific receptor. There is very little overlap. There can be some, but there's very little overlap. Now, obviously, this hormone is going to fit this receptor, and this hormone is going to fit this receptor. But there may be some additional activity that you can have a little bit of overlap, and bound hormones are not binding to the receptors. And there's a lot of, we'll talk about that in just a second, the binding proteins, how you're going to carry these things through the blood. And there's an allosteric site. And as we talk about enzymes, which is next up after hormones, we talk about enzymes, and then we get into mTOR. mTOR, a lot of these, all these things are enzymes inside of the, PKB, that's an enzyme. mTOR itself, it's an enzyme. And all of the, PI3K is an enzyme. So we're going to talk about enzymes and the nature of that and the inhibition and interaction of enzymes. And then we'll do proper mTOR signaling. But when something's bound, it's not going to bind to its receptor. And so think about IGF. Okay, the liver makes both the there are 6 different binding proteins. Binding protein 3, and they're easily named 1, 2, 3, 4, 5, 6. The 6 binding proteins for IGF. About 98% of your IGF is bound to them, and about 80% of all of your IGF is bound to binding protein 3. But the liver makes the binding proteins and IGF. But so again, steroid hormones, right? Androgens, they bind to an androgen receptor. So if the androgens bind to androgen receptor. So when people say like anabolic steroids, just androgens is a better name. Androgens is a better name for these things. And because they bind to androgen receptors, right? So if you are injecting testosterone, dihydrotestosterone, I don't know why you'd ever want to inject that, right? Unless you're a guy and you just really want to have difficulty peeing. If you want I just want the biggest, I want like a softball sized prostate. Give me some dihydrotest. Androstenedione, this is a precursor. This is sort of immediate precursor to testosterone. Dihydroepiandrosterone, DHEA. This is, you can buy this one at like a grocery store. I mean, you can probably go to S-Mart and get DHEA. It has some effect. It's not that much of effect compared to testosterone, right? Testosterone, you go to prison if you have that. Now you go to prison if you have androstenedione. And I don't know why anyone would have dihydrotest. But exogenous steroids outside of your body, right? Exogenous steroids, this is just outside of your body you're doing this stuff. Endogenous just means within. Endorphins, right? Endogenous morphine, anything endogenous, that's something you were making. Exogenous is just you eat it or you inject it or something. Remember, you can't eat your protein hormones. You go eat all the growth hormone you want. You might a hamburger will taste better. It's the same thing. So this is the pathway to get to your testosterone. Again, you can convert testosterone into dihydrotestosterone. I would prefer not to. This is if there's a question about what androgen is the interacts with skeletal muscle tissue the most or something like that, testosterone, or what is the hormone the single hormone that's most important for the regulation of muscle tissue, something like that, it'd be testosterone. Now, aromatase enzymes will convert testosterone to estradiol. This is particularly potent estrogen. And so people who are taking testosterone, or taking some sort of anabolic androgenic steroid, may try to take a aromatase inhibitor at the same time, and an estrogen blocker or something like that. Just take a aromatase inhibitor. So aromatase enzymes are going to do this conversion. But yeah, so you go, here's DHA, dehydroepiandrosterone, right, to androstenedione, to testosterone, and hopefully this is going to bind to your androgen receptors, but also downstream from cortisol. Aldosterone, kidney stuff. This is, hydration, sodium, and cortisol. We all know what that is. So these things are just, they're made from cholesterol. I mean, you can see what cholesterol looks like, and then just look at any cholesterol here, and then look at any of these hormones, of these steroid hormones. Is just, cholesterol with some stuff on it. And again, they are fat soluble, and they go right through. And again, cholesterol is not fat. Cholesterol and fat are not the same thing. Fat has a bunch of calories, and cholesterol does not. 9-ish calories per gram for fat, and cholesterol does not. It's this waxy thing that's any animal you eat is going to have in their membranes, they will have a bunch of cholesterol. So there can be really low fat food that's super high in cholesterol. Go eat shrimp. Look at, just Google, a food label of shellfish, of shrimp or something, and the cholesterol is outrageous and the fat is practically missing. And so it's these are different things. But again, it goes in, and you're looking at having the receptor. It's not a cell surface one, but so the receptor is in the nucleus, or maybe just the cytoplasm, but it also has cell signaling cascades as a secondary effect that it is working with. Okay, so autocrine versus paracrine. Endocrine is just get it into the blood. Put it in the blood, it circulates. And so that's most of these hormones are behaving in that way. If there's a hormone you're thinking of, it's probably behaving in that way. Paracrine is adjacent. Right? One cell releases this thing, and it doesn't leave its neighborhood. Right? For you, if you go on a walk, let's say this is 1962 outside, and you're going to go borrow eggs from your neighbor. Right? You're not going to get in your car and drive out to Lodi, to borrow eggs. You're gonna walk to your neighbor. If you hate your neighbor, you go across the street, and or whatever, catty corner or something. By the way, kitty corner is not an expression, that has nothing to do with cats. But so you go out and to some neighbor's house or something, and so that's paracrine. That's one cell releases it, and it's in the vicinity, right, in proximity to that cell. You're having your effect. Autocrine, you release it, and it binds to itself. It binds to itself and does its own cell signaling. So one cell releases it, binds to its cell surface receptor. Now, why doesn't it just do intracrine? Why doesn't it just, like, well, we have this thing inside, why don't we just have that be enough? It's already there. Why do we have to release it and rebind it? Well, because that cell signaling cascade has to be activated. That's how it actually works. Intracrine would be like, having its effect from inside. But so autocrine, paracrine, endocrine, this is really how things work. I mean, autocrine and paracrine. I mean, stuff like myostatin can work with, in all three situations, all three of those. So autocrine, paracrine, and endocrine. But yeah, so as long as you know the difference in how those work. Now, okay, back to the idea of binding proteins. They will prolong the half-life. These half-lives, I mean, the sort of lifespan of these hormones can be pretty brief. And carried on a binding protein can prolong that a little bit. Now, some of these binding proteins can be used as drugs or ergogenic aids. So myostatin we'll talk about, not yet, but we'll talk about at length of what it's doing, and how it's inhibiting PKB, and its roles in the body. And so it's a inhibitor of anabolism. uh, Myostatin is an inhibitor of hypertrophy. So just bind it to follistatin. Follistatin is a binding protein, and it deactivates myostatin. So if you bind your myostatin to follistatin, it deactivates it. Now you're going to get an anabolic effect. Now, is follistatin A hormone? No, but it is a anabolic agent. It's just a binding protein, though. So most of these hormones, as they circulate around in the blood, are bound to binding proteins. All right. Second messenger systems, signaling cascades, signal transduction, whatever you want to call this. We've talked a little bit about mechanotransduction, cell signaling cascades. This is really what the bulk of the semester now is going to become about this. And we all know Carl Corey, right? He and his wife, Gertie, they figured out the Corey cycle, which is you go through a bunch of carbohydrate metabolism. And here's a question. So enzymes and hormones have a lot of overlap. Yeah, enzymes and hormones are typically working through enzymes. A lot of enzymes are in these signaling cascades. I mean, you'll find a lot of enzymes in these signaling cascades, and so I promise we'll get there. But so the Coreys, Carl and Gertie, they figured out the Corey cycle, and you don't need to know what this is, but it's just you burn a bunch of carbs, create a bunch of lactate, send that lactate to the liver, burn a bunch of fat, convert it back into carbohydrate, and send it back to the muscle. So that's the Corey cycle: is you break down carbohydrate, make a bunch of lactate, send it to the liver, convert it back into carbohydrate, send it back to the muscle, and it's not a very metabolically efficient way of going through the day, but your muscle and liver assume you'll eat a meal today, and you'll make up for it. So in his lab, in Corey's lab, he had Earl Sutherland, and this guy is the one. You don't need to know his name, but he's the guy who identified the first ever signaling cascade, second messenger molecule, cell signaling, how all of this stuff works. He's the one who identified the first thing, which is cyclic AMP. And you've seen this before, PKA signaling. So he published 4 papers about it, about phosphorylation states. Enzymes can be turned on or off based on whether you phosphorylate them. I mean, just there's a light that's on right now in my kitchen. I can turn it off by flipping the switch, right? So if I phosphorylate my light switch, I can. So right now I have an overhead light that's on. I think that's this switch. And so I can phosphorylate this one and it turns off. I can phosphorylate this one and it turns on. So when you phosphorylate something, when you attach a phosphate, you use a kinase and phosphorylate something, you can either turn it on or off. And with PKA signaling, it's a bunch of cyclic AMP, and so that's what he identified. And we're in the liver here for glucagon. Is this is let's mobilize carbohydrates using protein kinase A, PKA. Now you've seen adenylyl cyclase before. Remember in the nerves when we were talking about opioids and cannabinoids having opposite effects, opposing effects on adenylyl cyclase and this signaling cascade, right? So PKA signaling, than did prostaglandins in a nociceptor. That's all we're looking at here, but we're not in nociceptor, right? We're in the liver. So glucagon binds to a cell surface receptor. So it says glucagon or epinephrine. A beta adrenergic receptor is for epinephrine. They bind to different receptors, but they do the same signaling cascade. The same signaling cascade is going to happen with glucagon or epinephrine. These are both catabolic. They are both going to break up your energy stores and get them on the march. So glucagon binds to its cell surface receptor. It's a G protein coupled receptor. It activates adenylyl cyclase. Adenylyl cyclase converts ATP into cyclic AMP. I'll show you what that stuff looks like in a little bit. It doesn't really matter. But so cyclic AMP binds to protein kinase A. Bind 4 of those to PKA. You activate PKA. So PKA is off, and you bind. So this little maroony color, that means off. Cyclic AMP binds to protein kinase A that activates it. PKA, protein kinase A, it's a kinase, it phosphorylates stuff, phosphorylates lots of things. So glycogen synthase is already on until you phosphorylate it, and that turns it off. But this is putting glycogen together. Glycogen synthase is putting glycogen together. It's taking sugars and let's go into storage mode. But PKA is catabolic. It's not let's go into storage mode. Let's build up our protein and our carbs and that's not what PKA is doing. PKA is breaking it up. And so you don't want to be putting money in the bank while you're pulling money out of the bank, which is what glycogen phosphorylase is doing. So protein kinase A phosphorylates a couple of things here, which is phosphorylase kinase. It sounds redundant. Protein kinase A phosphorylates phosphorylase kinase. That turns it on. Phosphorylase kinase phosphorylates glycogen phosphorylase, which turns it on. And now glycogen phosphorylase is chopping little glucosey chunks off of your glycogen. So you're chopping little chunks off of your glycogen, and you're not putting those chunks back together. You're not putting them back together because you've shut off glycogen synthase. So that's what was discovered in Sutherland's lab is PKA and its catabolic role in uh, glycogenolysis, right, through glycogen phosphorylase, but identifying cyclic AMP as a second messenger molecule. Cyclic AMP, second messenger. Now let's go into a fat cell, right? Epi, norepi, they bind to a beta adrenergic receptor. Same thing. You see the exact same signaling cascade. Adenylate cyclase over here converts ATP into cyclic AMP. These guys are going to bind to PKA. And once they bind to PKA, PKA is going to phosphorylate a ton of stuff, but it's going to be different stuff if you're in an adipocyte. And this diagram, this is sort of the popular diagram on the internet. It's a little bit simple. It gives this impression of hormone-sensitive lipase being the enzyme that will really initiate lipolysis from a triglyceride to a diacylglycerol, triacylglycerol, diacylglycerol, monoacylglycerol, right? So if you have like a triglyceride, you have glycerol, a 3-carbon carrier, and then you have 3 strings of free fatty acids, 3 free fatty acids connected to that 3-carbon glycerol, that carrier. That's a triglyceride or triacylglycerol. Adipocyte triglyceride lipase, that's the enzyme that does the first one. And then hormone sensitive lipase that it shows there, that's the enzyme that does the second one. And then over here, you see monoacylglycerol lipase. That's the one that does the last one. And you're just freeing little fatty acids off of this triglyceride. And so PKA is getting these things phosphorylated, initiating lipolysis from adipocyte triglyceride lipase to hormone sensitive lipase and perilipin. Perilipin is this coat on the lipid droplet, and it's sort of protecting it, and you have to open that coat. You have to expose the triglycerides. You have to expose them so that the enzymes can go do their lipolysis, their lipolytic activity, their lysing. So PKA is also phosphorylating perilipin, the coat. And so it's just like, every Halloween, there's some creepy guy who goes around. There's an Office episode about this, like some guy exposed himself to Pam or something. And Michael Scott was giggling and whatever, you know the story in life. And last year on campus at Pacific, some guy dressed in like a Spider-Man costume did it. I mean, maybe it's just like an anatomist who's trying to get students ready for for college. But this creepy story of there's like some guy exposed. That's perilipin. You're all snug and covered, and then you get phosphorylated, and this happens. That's PKA to perilipin, and that's really going to get the lipolytic process started. And then you can go through actual lipolysis, not with perilipin, but with the lipolytic enzymes. So that's PKA working. So now insulin, in this same diagram, we see insulin, and we see it subtracting that little minus sign, cyclic AMP. So we think of insulin as inhibiting lipolysis. Insulin inhibits lipolysis. So what is lipolysis regulated by? Well, growth hormone, catecholamines. That's this catecholamines, epi, norepi. So we know it's regulated by catecholamines. We don't need to talk about that. But insulin, that's the next one on the list. We'll talk about growth hormone in a few minutes. And glucagon, right? We already talked about that. Glucagon would do the same thing as epi, norepi. Glucagon does this signaling cascade. So let's rule out glucagon and catecholamines. But insulin, we see its effect on cyclic AMP. This goes through something called phosphodiesterase, PDE, PDE3B specifically. But let's talk about the pancreas first. Don't write this down. Take a breather, take a minute, and this is just story time. So the pancreas, the pancreas, anything pan, a panoramic, pan anything is just like all over the place, right? So pan's all, and then flesh. So the pancreas is all flesh. That's what it's named after. So, panorama or panoramic, you're seeing everything. A panacea, that's a cure-all. You don't see a lot of cure. Exercise is a panacea. Maybe you see it in that context. A pandemic, we're looking at this today. A pandemic with COVID, it's affecting everybody. There's nobody immune. There's no country or class or demographic or age or whatever that is immune. It's a pandemic. It's everywhere. Demographic, it affects all people, right? You know what demographic means. Demography, demographic, whatever, it affects everybody. Panphobia, right? You have this sort of fear of everything. The pantheon is the temple of every god, right? The pantheon, the temple of every god. Pandemonium, that's sort of reserved for World Wrestling Federation or World Wrestling Entertainment or whatever, WCW and WWE, those refs. It is pandemonium in here, right? As that's what they shout in like every single match. Just watch an old The Rock versus I don't know any of the other ones. Watch one of those, and Steve Austin. There's another, and there will be pandemonium at some point. But that's literally, this is pan demon. It's like the house of all demons. This one's interesting. This one's funny because some of you are wearing pants right now, and you can wear whatever you want when it's all like waist up. You can put on your tie, your collared shirt and tie, and then just be wearing shorts or boxers or whatever underneath. For those wearing pants, where did that word come from? And it does come from pan. So Pantaleon, right? This is all compassionate, and so he was the patron saint of Venice, right? But it was this popular Venetian name. And in the 16th century, sort of the 1500s, Commedia dell'arte was this play that had, I love Mike Tyson's Punch Out, the video game, but it is super racist because everybody is every character. I mean, it came out in I think 87, and every single character is this really stereotypical. Soda Popinski is the Russian guy whose original name in the arcade was Vodka Drunkinsky, and he's like constantly drinking, and he's drinking vodka. But there's these like racist sort of stereotypes, and the Commedia dell'arte was similar. It had this stereotypical Venetian character, and Pantalone, that was the character, and he wore pants, right? He wore these sort of one-piece pants, and so they started calling them pantaloons. So that's where pantaloons came from, and it was shortened to pants. So it literally means all compassionate. The word pants, if anyone's wearing pants, you are wrapped in compassion. That is the root word of pants, is all compassionate. I don't know what underpants would be. Not everything with the word pan in it is everywhere, all whatever. I mean, it's pots and pans. That's not everything. But panic is fear of the Greek god Pan, who played the panpipes. So panic is not you're like afraid of everything. So pancreas, all flesh. This goes everywhere. So with the rooster testicle, example, with that experiment, we have this idea of a hormone affecting global growth and metabolism, and Berthold was the founder of endocrinology by saying, well, let's get rid of this thing and notice what its effects are. And they did the same thing with the pancreas, right, in dogs as opposed to chickens, and it became diabetic, and all tissues are affected. And So what is insulin actually doing, right? We're still on fat metabolism is still what we're talking about, regulators of fat metabolism. We talked about glucagon and we talked about catecholamines, epinephrine, norepinephrine. So insulin receptor substrate, PI3K, for some reason it's not in the huge bold one, and PKB. So these are a few things we've talked about so far. IR stands for insulin receptor, and I actually don't like this diagram because technically, PKB, that's what this is, goes to mTOR, mammalian target of rapamycin, and this arrow doesn't go straight there. This arrow should go here, and then that arrow goes there. And so, like the diagram isn't very good, but this little part is nice. Where insulin receptor substrate, PI3K, PKB, downstream from PKB, you see GLUT4 mobilization. But there's something else that happens downstream from PKB that's going to cause this effect. She is wearing a swimsuit, just she happens to have picked a skin-colored one. But the lower the person's body fat percent, the better insulin sensitivity. There's a question: is the pancreas a gland? It's an organ, but it works as a gland. It's one of those hybrids. I would say it's more of a gland than the liver is. The liver has glandular functions. The kidney is almost pure organ, but a little bit of glandular function. And the pancreas is really close to just straight gland. Yeah, I would lump it more of a gland than an organ. It gets a little bit hazy in that space. So the better your insulin sensitivity, the lower your body composition. If you just take everyone in the world and line them up and measure their body composition, you'd have a pretty good look at what their insulin sensitivity is. Higher body fat percentage tends to correspond to, it's not a perfect, it's like y equals mx plus b, like high school algebra, like a perfect line. It's not that ideal. I mean, there are variants here, but as people's body fat percent gets higher, men and women both, you see higher and worse insulin sensitivity. Now, what we see here is insulin to cyclic AMP. Phosphodiesterase is cyclic nucleotide phosphodiesterase or phosphodiesterase or PDE3, specifically 3B, even more specifically. So if you have, epinephrine, norepinephrine, getting this thing started, we get adenylate cyclase. Sometimes it's adenylol, sometimes it's adenylate. That's the exact same thing. Just like you see AKT and PKB, exact same thing. AKT, PKB, those are just interchangeable terms, especially when we get into mTOR and we see like P70S6K and S6K1. There's all these names for the exact same thing. And so just bear with me in the sort of bad nomenclature of the sciences. Adenylol or adenylate cyclase converts ATP into cyclic AMP. We need cyclic AMP to bind to pKa. Let's say pKa is over here. Cyclic AMP is what binds to pKa. AMP doesn't. Cyclic AMP does. So phosphodiesterase converts cyclic AMP into AMP. AMP doesn't bind to pKa. And so that stops pKa signaling. Phosphodiesterase stops pKa signaling. Now, if you can turn it on, now this is 1968. Don't read this. Just understand that influence of insulin on phosphodiesterase has been studied since the 60s. This is not a new concept that insulin is affecting lipolysis. And so we have a bunch of receptors that stimulate adenylate cyclase. We have receptors, these ones. We have receptors that inhibit adenylate cyclase. And so you'll recognize some of this stuff, the stimulation and the inhibition, the beta adrenergic receptors. You know that, right? We just talked about that, beta adrenergic. This is epinephrine. But remember that opioid stuff, opioid, cannabinoid, the adenylate cyclase right here. This is that nerve you should remember. So there's stuff that's going to stimulate adenylate cyclase, go ahead and throw prostaglandins, and there's stuff that will inhibit it. Once you have adenylate cyclase, once this is activated, you've made cyclic AMP. You're breaking down your ATP into cyclic AMP. Now, PDE, phosphodiesterase, can come in and convert it into ATP, and it obstructs that cycle. It obstructs that signaling. So this is phosphatidylinositol 3 kinase, PI3K. This is one of those things you'll have seen a few times. PKB, protein kinase B, you'll have seen this a few times. PI3K is upstream from PKB. We'll talk about wart mannan. It's a metabolite of a fungus that grows on pineapples. It's a PI3K inhibitor. But there seems to be multiple ways in which insulin is inhibiting or is activating your PDE. It seems to come from both PI3K and PKB. Now, downstream from PKB, that is GLUT4 translocation, but PI3K and PKB are both seem to be activating phosphodiesterase. So if you activate phosphodiesterase, you convert your cyclic AMP into AMP. AMP does not activate PKA, so lipolysis doesn't happen. So if you have insulin in your system, if insulin is currently in your system, you are not burning fat, right? You are not burning. So go eat a bunch of carbs, then go exercise, go get on the treadmill. Yeah, you'll start to get rid of insulin, or if you get on the treadmill fast enough, maybe you can do um, non-insulin dependent glucose uptake and stuff. But the answer to this question is it makes things a little bit trickier. So GLUT4 translocation signaling pathway can become resistant to the effects of insulin, poor insulin sensitivity. Does that affect PDE sensitivity too? And yes, there's PI3K, there's PKB. Those are the things that are doing it. It gets a little bit trickier. Looking at things like lipoprotein lipase, looking at things like glucagon suppression. Let's just finish up a couple of slides really quickly, and then this will be it, just so we can go through the rest of these. I'll just really quickly. Glucocorticoid, right? Glucocorticoid receptor. So cortisol, this is cortisol right here. We're stopping PDE3B, that is specifically the fat metabolism version, so PDE3B. But then also with cortisol, there's additional effects. We have an autocrine signal to increase PKA on top of inhibition of PDE. So we are decreasing PDE expression, and we're stimulating lipoprotein lipase activity. So it does get a little bit messy, but then we also are the transcription. We are transcribing lipolytic enzymes at the same time, and so cortisol does mobilize fat. It's sort of bad at this stuff. Over here, we can see, I don't know where, there it is, cyclic AMP. So we're increasing cyclic AMP with tumor necrosis factor. It's a protein, and then growth hormone. There's a bunch of different things growth hormone is doing. Nobody's outlined these all that clearly, but beta adrenergic receptor signaling seems to be a big one for its effects. So let's stop. What questions do we have? Anyone have some burning curiosity? We are absent the flames of curiosity today. I was so tired today. I don't know what did it to me. And so I hope you are at least as alert as I am. But I will, I'll see you on Friday. Let me know if you have questions between now and Friday.
Will do.
All right. See you, everyone.
All right. See you Friday.
Thank you.